All right, let's continue our discussion with the equations of lines in 3 space. And let's start by working through an example. So we want to find the equation of a line that's passing through this point, 2, -3, 1, and is parallel to the vector I minus 2j plus 2k. Now remember what we needed. Our equation was r, my vector, is equal to r naught plus TV, where r naught was the position vector pointing towards my point. So starting the position vector ending at the point 2, -3, 1. So r naught would be equal to 2, -3, 1. And my vector that my line is parallel with is 1, -2, 2. So as long as we know these things, we can write the equation of our line. So let's move over to our new board, and we get that r is equal to r naught plus TV, and let me go back to make sure I remember what that was. 2, -3, 1. Oops. So 2, -3, 1 was my position vector, that r naught, and v was 1, -2, 2. So my vector r is 2, -3, 1 plus t times 1 minus 2, 2. And remember, this was my vector equation of my line L. And if I wanted to write the parametric equations, I would get x is equal to 2 plus t, right? So that's my x naught plus t a. My y is equal to -3 minus 2t, and z is equal to 1 plus 2t. And these are the parametric equations of my line, and this is my vector equation of that line. So, to recap, let's go to a clean board again. If I have r, which is x, y, z, it's equal to my position vector of my known point, x naught, y naught, z naught, plus my parameter t times v, which is the directional vector that's parallel to my line L. That's my vector equation of the line, and then I know that my parametric equations are x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. Now, those are the two that we learned in the last video. And we could do one more thing here, and that is to write the equation of this line by eliminating my parameter t. So if I solve for t in each one of these equations, then they would all be equal to each other, right? They'd all be equal to t. So what does that give me? That gives me that x minus x naught over a, so what is t? Right, it's equal to, I could move my x naught over and divide by a. It's also equal to y minus y naught divided by b, which is also equal to z minus z naught divided by c. And these are actually called the symmetric equations of my line L. Okay? So we've learned the vector equation of my line L, the parametric equations of my line L, and now the symmetric equations of my line L. All right, we want to talk about one more thing with lines before we move on to our discussion about planes. And that's going to be, let's go to a new board, a line segment. Not a line, but just a line segment in 3 space. So let's draw our 3-dimensional coordinate system. There's y, there's x, and there's z. And we have our line L here, but instead, let's say that we want to define the line segment between 2 points who have position vectors r0 and r1 respectively. So this time we know these 2 points r0 and r1, and we define the vector v this time to be the difference between r0 and r1. So R1 minus R naught. All right, and we see that that is this vector right here, which is clearly parallel to my line L. So if this is, so what does that tell us? That tells us that R is equal to R naught plus TV, which is equal to R naught plus T times R1 minus R naught. All right, so what does that give us? We have R equals R naught plus TR1 minus TR naught. Or if I group my like terms together, I get 1 minus T times R naught plus TR1. Alright, so here's my equation. And if I restrict T to run from 0 to 1, that will give me just this portion of my line L. So this right here is the line segment from R naught to R1.